This is 4.3, where we're going to look at logarithms. We've already studied inverses and exponentials, and so this kind of combines those two ideas because a logarithm is an inverse of an exponential. So we just last time in 4.2 talked about the exponential function y equals 2 to the x. Now if we try to find the inverse of it, remember we switch x and y, so we get x equals 2 to the y, and then we're supposed to solve for y. Well, how do you solve for something that is an exponent? Well, we can't without logarithms. So the problem that we run into is that there's nothing that we currently know to get that exponent out of the exponent. So when you have something in exponential form like b to the y equals x, we can switch it around into log form. Notice that the exponent comes by itself, the base goes to the base of the log, and what the exponent was equal to goes inside the log. So all of those same components, but now the y is by itself, which is what we wanted it to do. Graphically, when we looked at exponentials, we knew that they curved up like that for an exponential growth. If logs are inverses, we studied that inverses are reflections over the line y equals x. So a log would look like that. So we have our exponential on top and then our log on the bottom. And that's for exponential growth. They would look slightly different if it was exponential decay. So let's take a look on how we're going to graph some of these logs. Here we have log of x base 3. So if you remember when we did exponentials, we graphed the points 0, 1. I'm sorry, I said it. I wrote it. We graphed the point 1, 0. Sorry. That's what we're going to do for logs. Exponentials, we did 0, 1, and 1b. But since we're doing their inverse now, this is what we did for exponentials. We're going to do 1, 0, and b, 1. Because we're switching them, switching the a and the b. So for this particular graph, since it's a log, it's going to go through 1, 0, and 3, 1. Because our base is 3. So 1, 0, 3, 1. Its asymptote this time is the y-axis, opposed to last time where we had it as the x-axis. The domain is 0 to infinity. The range is negative infinity to infinity. You'll notice that those switched from the exponentials. On exponentials, it was the other way around. And then our asymptote is x equals 0. On the exponential, it was y equals 0. So everything is switching. Just like with the exponentials, our logs can also be transformed. When you have a plus 2 inside of the log, that means it's going to move left 2. So we're going to take those original points that we talked about up above, the 1, 0, and the 3, 1, and we're going to move them both left 2. So negative 1, 0, and 1, 1. Which also means that our asymptote, oops, I put a y. It is not y. Remember, for logs, it's x equals, and since it's moving left 2, it'll be x equals negative 2. So we'll put that asymptote on our graph. Graph the point negative 1, 0, and 1, 1. And then we'll still have our curve. Domain is now negative 2 to infinity, but our range goes negative infinity all the way to positive infinity. All right, let's try a couple more graphs with some transformations, all using those same original points and just transforming them. Notice this time that our plus 2 is on the outside of the function. When it's on the outside, that tells us that we're going to move up 2. So we're going to take those original points, 1, 0, and 3, 1, and we're going to move them both up 2. So 1, 2, and 3, 3. When you move something up, it doesn't affect your asymptote. So our asymptote is still going to be the y-axis. It just shifts our points up 2 spots. So that means our domain is the same as our parent function, and our range is as well. Now number 4, we see that plus 2 on the outside again, so we know that we're going up 2, but there's a sneaky negative in front of our log. Remember, when it's on the outside, that reflects us over the x. So we're going to take our points, 1, 0, reflect it over the x, which changes your y, so 1, 0 isn't going to change, and then move it up 2, 1, 2. Do that with our other point, 3, 1. Reflect over the x, your x stays the same, but your y changes, so the 1 goes to a negative 1, and now we're going to move it up 2, so that's 3, 1. So you can also do that on the graph. If your original point is 1, 0, reflecting over the x-axis keeps it right there, then move up 2. Or if you had the original point 3, 1, you reflect it down to here, and then move up 2. Our asymptote doesn't change because we didn't move left or right at all, so it is still our y-axis. But we reflected it, so instead of having it point down on the asymptote, it's going up. Domain, 0 to infinity, and range, all real numbers. All right, let's switch gears. Now we're going to talk about evaluating logarithms. But we're going to do this without a calculator. So when we're asked to evaluate logs, we need to switch them to exponential form. So that switcheroo that we were talking about at the beginning. So we're going to set it equal to x, and then to switch it, you always take the base, so 4, to the exponent. This number out here is always the exponent, and then set it equal to the argument. That 16 is called the argument. Okay? Now I think most of us probably know that what 4 to some power gives us 16. We know that it's 2, but as they get more complicated, there's a concept I want you to get more comfortable with, and that's getting your bases to be the same. So I can rewrite 16 as 4 squared, because 16 is 4 squared. Notice now that I have a 4 as a base and a 4 as a base. Once your bases are the same, your exponents are equal to each other. So we know that x equals 2. Let's try some more of those, where we're going to start in log form, switch them to exponential, get our bases the same, and then our exponents will be equal. So we have log of 1/4 base 2. We're going to set it equal to x, take our base to the exponent equals 1/4, and we want to get our bases the same. So we want this 4 to be a 2. So we know that 2 squared is 4, but we don't want it in the denominator. So if you remember your exponent rules, to get it back up to the numerator, we could make it a -2. See how our bases are now the same? Once your bases are the same, your exponents are equal to each other. So we'd say x equals -2. All right, log of 4 base 16. Set it equal to x. Take your base to the exponent, and it's going to equal your argument. Now we want to get our bases the same, so we need to rewrite 16 to have a base of 4. So 4 squared, the x is still there. So now our bases are the same, and we want our exponents to be equal to each other. This one doesn't have a shown exponent, it has an imaginary one, a 1. So we're going to say 2x equals 1, so x equals 1/2. All right, log of 1 base 9, set it equal to x. 9 to the x equals 1. This is one of those where we can't get the bases the same. This is a special case where we just have to know anything to what power is 1. Well, if you said 0, you were right. So anything to the 0 power is 1. So our x would be 0. All right, see if you can try this one. See if you can hit pause, switch it around, get the bases the same, and then set the exponents equal to each other. And then come back and check. So you should have done 1/4 to the x equals 64. We want to get our bases the same. So we want to get this 4 to be on top. So that's going to be a negative x. And then this one is 4 to the 3rd. Our bases are the same, which means that our exponents are equal. So negative x equals 3. Divide by negative 1. X equals negative 3. All right. Then we have log of 8 base 8. Set it equal to x. 8 to the x equals 8. Our bases are already the same, making our exponents equal. So x equals 1. Anytime your base and your argument are the same, it will always equal 1. All right, last two, we're going to evaluate these with a calculator. So grab your calculator, find your log button, hit log 20, see what it gives you. It's going to be an ugly number, so we're just going to approximate here. Log of 20, you should get 1.30. And then find your ln button. ln is another log, the natural log. I want you to approximate the value for a natural log of 80. Hopefully you get 4.38. So pretty easy to use your calculator with those. Just want you to be familiar with where those are on your calculator.